And here in problem 31, they give us a function f of x as x minus the log of x. Okay. I'll leave some room for my drawing. And so my first derivative information, f prime. The derivative of x is 1. The derivative of log x is 1 over x. Which reminds me to say, by talking about the log at all, you can't have the log of a negative number. In fact, you can't have the log of 0. So by merely talking about the log at all, we're assuming that x is greater than or equal to 0. Otherwise, it doesn't make sense. And indeed, you see here, x couldn't be 0. 1 over 0 is not defined. So, we set this equal to 0 in order to solve for the critical points. Is it clear x is 1? 1 minus 1 over x equals 0. What's the only value of x to make that 0? Is x equal to 1? So we have a critical point here. And I need the y coordinate. I need f of 1. Go back to the original. 1 minus the log of 1. But you remember the log of 1, right? It's 0. Do you remember why? That is sort of important. Maybe I should. The log of 1. Let's say that it equals a. I want to show you that a is 0. Well, here we've got a logarithmic equation, right? And you remember the way we solved? This was on the midterm. Remember the way you solved a logarithmic equation? You made both sides powers of e. So e to the log 1 is equal to e to the a. But e to the log anything, that's the identity. We call that identity 2. E to the log of anything is that thing. And so what's the power of a? What's the power of e that gives you 1? The only way a power of e or any power would give you 1, e to the 0. E to the 0. So that's why the log of 1 is 0. That's sort of an important number fact you should remember. Crops up a lot. Nota bene. E log of 1 is 0. And I'm not sure did this chapter talk about asymptotes? No, it didn't. It didn't. Okay, so I won't. Usually in Calc 1 we talk about asymptotes at this point, but it's not in 5.1. Maybe it's in 5.2. I'll look later. Okay, so we have found our critical point, and let's draw it. Remember, I only need to worry about x as being positive because the log doesn't make sense for non-positive numbers. So where x is 1, y is 1. So let's say 1, 2, 1, 2. So where x is 1, y is 1 here, you've got a critical point. And so 1 point, you got 2 intervals. Let's do our shape intervals. Over each interval, we're going to test the first derivative to conclude at one point to conclude something about the shape. Two intervals. Well, left of 1, which has to be bigger than 0. Remember the very nature of logarithm. You can't have x go south. And then to the right of 1. So let's test a point, let's say f prime of a half. So that is 1 minus 1 over a half, but that is 1 minus 2. The point is that it's negative, so the shape is decreasing. Let's try f prime of 2. That's 1 minus a half, which is positive. Therefore, the shape is increasing. So draw decreasing on the left, increasing on the right. Yeah, that's good enough. It's not quite true. So remember the graph of the log. If you just graph the log alone, it would look like that. So the log of a small number is becoming increasingly negative. That's why you've got this asymptote there. So there you have increase, there you have I'm sorry, no wonder I'm hesitant. I got it backwards. The way I've drawn it, I've made it increasing on the left. I got this here backwards. And I got it decreasing on the left. I got these things switched. Yeah, sorry about that. Because if you want something which is decreasing, it has to look like that. And if you want something increasing, it's got to look like that. Sorry about that. You're decreasing on the left and you're increasing on the right. And because this log is asymptotic, that's why you've got an asymptote here. But the chapter didn't talk about asymptotes, so that's all right. But let me say this. What we're doing, you know, in the next chapter 5.2, we're going to be talking about concavity. I talked about that a little the other day. And basically, there are 4 shapes. And we're drawing one of these 4 shapes over each interval. So you got 2 possibilities for direction, increasing, decreasing. You got 2 possibilities for concavity. Concave up, concave down. We talked about that yesterday. And we'll do problems coming up today. What does an increasing concave up shape look like? Increasing concave up looks like that. What does increasing concave down look like? That's an increasing concave down. What does decreasing concave up look like? What does decreasing concave down look like? So when we put concavity into the picture, we're going to be drawing one of these four possibilities over each interval. And number 36. Is that going to be surprising? So 5.1. Let me talk to myself first. I've got e to the negative x squared. So I'm going to do that first derivative business real soon. But I'm thinking in my own mind first. You know, I know what e to the x looks like. And so if I make it e to the x squared, it's just steeper. But now I'm going to make that negative. E to the negative x squared. You remember that a negative root means reciprocal? So big numbers become small, small numbers become big. Okay. So I built up my graph simply so I wouldn't make that same mistake. So the purple is what I'm expecting to come out with. So now let's do it. There I was talking through my hat. Now let's do it. 5.1, 10, 11, 31, 36. Gives us f of x as e to the negative x squared. Okay. So let's get my first derivative, f prime. So this is a chain rule problem. E to the negative x squared, e to the box times the derivative of the inside is negative 2x, right? Chain rule. Shall I remind you of the chain rule? If you're taking the derivative of e to the box, first it is its own derivative, e to the box, but then secondly you multiply by the derivative of the inside. So the derivative of negative x squared is negative 2x. So this is negative 2x e to the negative x squared. Okay, I'm good. So you set this equal to 0. And remember, e to the box, that's never 0. That's never 0. Remember the graph of e to the x always looks like that. So this is never 0. The only way the product could equal 0 is if x is 0. So you've got one critical point. And I need to graph it. F of 0, go back to my original. If I put 0 in, e to the 0 is 1. So, 1, 2, 1, 2. When x is 0, y is 1. There's my critical point. Now, this is a good problem because I'm thinking ahead to the next step. And why? Oh. No, I'm okay. Yeah, I'm okay. What is throwing me off here where I was talking through my hat, that's garbage. I'm okay. So I got one critical point, I got two intervals. So let's do our intervals. Over which I'm going to test one point to conclude something about shape. My black is correct, my purple is not. And so one critical point at 0. I have an interval to the left of 0, and I have an interval to the right of 0. So let's test my derivative at, I only need to test 1 point. Let's say -1. F prime of -1 becomes, right? -2 times -1 is +2 times e to the, well, that's always positive. That's a positive number, and so my shape is increasing. And f prime of, say, +1, that would be -2 times +1, that's -2, e to the -1, that's a negative number. So it's decreasing. So I need increasing on the left, decreasing on the right. And if you just drew, at this point, you would know nothing better than to draw increasing on the left, decreasing on the right. So if you drew the red, I couldn't fault you for it, because so far that's all the information you've got. In fact, in 5.2, when we learn about concavity, we'll learn that this thing is actually doing this. But as I say, as a 5.1 problem, all you know is increasing and decreasing. And so if you drew the red, I couldn't fault you at this point. In order to see the green, we need 5.2. All right, so let's go to 5.2. Now with the second derivative, that tells us the whole story. Yeah. Okay, let's go to 5.2. Now, problem 19 is really a vocabulary exercise. It's not really a homework problem. You're going from the picture to the intervals. So here in problem 19, find the inflection points, concave up, concave down. Okay. So in number 19, we're starting with a picture. And I think this is what they're drawing. 1, 2, 3, 4. So I think they mean to say that there is a vertical asymptote at 2. So I think they mean to be saying this. And then they mean to be saying this. So in your problems, you're actually going the other way. You start with the interval and draw the picture. Here, just to get you into it, they draw the picture and you do the intervals. So do you see that here on the left, that shape is concave down? That's what we mean by it bowing downwards. And here on the right, we call that concave up. That's where we're bowing upwards. And there is this asymptote at 2. And so we need to talk about asymptotes. Do you remember what an asymptote is? It's a limit line. The function gets closer and closer and closer to the line, but never touches it, never crosses it. And so in fact, this here is a vertical asymptote. That's a vertical asymptote. And you agree that f of 2, this does not exist. F of 2 is simply this vertical asymptote. There's no y coordinate for f of 2. F of 2 is just this vertical asymptote. It doesn't exist. And so we will call a vertical asymptote a default inflection point. I say default because f of 2 doesn't exist, but yet on the left you're concave down, on the right you're concave up. So concavity does change to either side of 2. So it acts as though it were an inflection point, even though it's just a vertical asymptote. And so if you do your intervals, normally we would test the second derivative at a point. We don't need to do that here because the picture is drawn for us. And we conclude something about concavity. So we have an interval between 0 and 2. We have an interval from 2 up to, well, I think they mean for this to stop at 4. I think they've got it drawn that way, 4. And so in this interval, it is concave down, and in this interval, it's concave up. This problem really is just easing you into it. They're trying to get you to identify these shapes. This shape is concave down, that shape is concave up. Okay, so now let's get into the heart of the matter. Let's look at 25. And as I look at my book, I have crossed out problem 45. Why? Why have I struck out 45? don't know why I crossed out 45. Well, we'll worry about it later. So let's do problem 25. So here they give us a function f of x as x cubed minus 3x squared plus 2. So I'm going to leave some room for my drawing, and I'm going to come down here, and I'm going to get all the information I can out of my first derivative. So that's 3x squared minus 6x. Okay? And you want to set that equal to 0 to find your critical points. Is it okay you could factor out a 3x, leaving you with an x minus 2? And you set that equal to 0. Do you see, a product is 0 only when the factors are 0. Do you see you got two critical points? X could be 0 or x could be 2. So you've got 2 critical points at x could be 0 or x could be 2. I need to plot them. So go back to the original f, put 0 in for x, you get a y coordinate of 2. Now go back to the original and put 2 in for x. What do I get? 8 minus 12 add 2. Is that negative 2? Okay, so there are my two critical points. So let's call it 1, 2, 3. So at 0, I have one critical point at a height of 2. And where x is equal to 2, I've got a y coordinate of negative 2. So there are my two critical points. That gives me 3 intervals. Always one more interval than you have points. So let's do the shape intervals, over which I'm going to test my first derivative at one point to conclude something about the shape. So left of 0, between 0 and 2, to the right of 2. I wrote this wrong. I said left of 0. That's left of 0. And in fact, sometimes I have students actually using the word. That's fine. If you want to say left, between, right, that's fine. That's fine. So let's take negative 1. F prime of negative 1. Well, sure, I could put it into here, but how about the factor form? If x is negative 1, the first factor is negative, the second factor is negative, they multiply to a positive, and my shape is increasing. Between 0 and 2, how about let's take 1? And again, I don't care about the size, I care about the sign. When x is 1, that factor is positive, that factor is negative. Positive times negative is negative. My shape is decreasing. F prime of 3, that factor is positive, that factor is positive. 2 positive give me a positive, and I'm increasing. So at this stage, you probably could guess, you know, This cubic curve, degree 3, it is at most a sideways S. And so at this point you probably could guess up, down, up. And you'd be right, but the instructions say go on to the second derivative. The second derivative is going to tell the whole story. F double prime is 6x minus 6. So you set that equal to 0 and solve for the inflection point. You have an inflection point at x equals 1. Are we okay? 6x minus 6 is 0, so x is 1. That means you got 2 concavity intervals. Over which we're going to test the second derivative at one point to conclude something about concavity. So if you have one point, the two intervals are, so I should also graph that. Let's also graph that. At 1, what's the y coordinate at 1? Go back to the original. That would be 1 minus 3 add 2, is that 0? So here at 1, maybe I could use purple. There is my inflection point. When x is 1, y is 0. There's inflection point. That's inflection. These are critical. And so one inflection point gives me two intervals. Left of 1, right of 1. And so take any value left of 1, say 0. If you put 0 into the second derivative, 0 minus 6 is negative 6 is negative, so it's concave down. F double prime of 2, take any number there. 12 minus 6 is positive, it's concave up. Okay, you now have filled in both tables. You now have filled in both tables. And now you can do the complete graph. These two tables contain all the information. So, I have 3 points that I've identified here in my drawing. Those 3 points talk about 4 intervals. Look each one of those 4 intervals up in this table, then in this table. So, left of 0. In this table, you're told the shape is increasing. Left of 0 is left of 1. So this interval lies inside here, and so it's concave down. I want to sketch an increasing concave down curve. Let me take a different color. I want to sketch an increasing concave down. So what I'm doing, remember when I gave you this table? Those are the 4 possibilities. And you are stringing each of these 4 possibilities between your points. So, between 0 and 1, an inflection point 1. That lies inside this, doesn't it? 0 to 1 lies within 0 to 2. So the shape is decreasing, but 0 to 1 lies in the first row here, so it's concave down. So I need to sketch a decreasing but concave down curve. Decreasing, concave down. Decreasing, concave down. That shape. Now between 1 and 2, 1 to 2 lies in the second row here. It lies in this row, so the shape is decreasing. But 1 to 2 lies in the second row here, so it's concave up. So I need to sketch a decreasing but concave up curve. And finally, to the right of 2, you're in the third row there, but you're in the second row there. So right of 2, the shape is increasing, but everything right of 1 is concave up. So sketch increasing concave up. And so you see you have that typical sideways S curve that typifies a cubic curve. Okay. I want to look a little something up here. Yeah. You know, I wondered why I scratched out problem 45. I think I scratched it out because of my own ignorance. I want to draw your attention to a sentence in the book. Let me see if I can zoom here. Let's see if I can zoom here. See if I can focus that. Okay. Question 45 has to do with the point of diminishing return. And that's an economic phrase, the point of diminishing return. Mathematically, it's what we call the inflection point. So we would characterize the inflection point as the point of diminishing return. So when problem 45 asks you for the point of diminishing return, they're just after the inflection point. Now, why? What does the point of diminishing return mean in terms of economics? We also see that the rate at which profits are increasing on the interval is itself decreasing. The rate at which profits are increasing is going down. The slope of the tangent line is smaller as you move. So P of t is increasing ever slower on the interval, which is why we would consider the inflection point the point of diminishing returns. Yeah. Does that make economic sense? You're trying to maximize your profit. But there comes a point of time in which the more you put into the making and selling, the less profitable it becomes, because it's costing you more in order to produce more goods. And so that's the point of the diminishing returns. So when when an economist asks about the point of diminishing returns, they're talking about the inflection point, because that's where the second derivative is changing from concave up to concave down. Okay, so that's what problem 45 means. So I guess we could do problem 45. But next up is 27. I don't think I'm going to finish problem 27, but let's set it up. So here we have f of x is equal to 4x to the fifth minus 5x to the fourth plus 1. So I'll leave a little room for my drawing, and let's go to my first derivative. 4x to the fifth becomes 20x to the fourth, and 5x to the fourth becomes 20x cubed. The derivative of 1 is 0. So there's my first derivative, and what do? I set the derivative equal to 0 in order to get my critical points. Now, doesn't that factor nicely? There are two terms. Factor out a 20x cubed. And you're left with x minus 1. Are we okay? Factor out 20 and x cubed. And so if you set that equal to 0, is it clear you have two critical points? At x could be 0 or x could be positive 1. So what's the y coordinate there? Go back to the original, put 0 in for x, you get 1. And here, put 1 in for x, and you have 4 minus 5, add 1. Do you get 0? So, if I sketch that much, 1, 2, 1, 2, 1, 2, when x is 0, y is 1. There's one inflection point. And then when x is 1, y is 0. There's the other inflection point. Sorry, critical point. Two critical points. So 2 points give me 3 intervals. Always one more interval than points. So let's do our shape intervals. Over which I'm going to test the first derivative at 1 point to conclude something about shape. So there are going to be 3 intervals. Because I want left of 0, between 0 and 1, to the right of 1. So let's take f prime of, say, negative 1. Now, in factored form, that factor is negative, that factor is negative. And if I multiply two negative numbers, I get a positive, shape is increasing. Now let's say I need a number in there between 0 and 1, say a half. That's positive, that's negative. Product is negative, decreasing. How about f prime of 2? Positive, positive. Product's positive, so it's increasing. Now let's get our second derivative. F double prime. Well, that would be 80x cubed minus 60x squared, 60. And so I set that equal to 0 for my inflection points. again, that factors nicely. How about I factor out 20? Yeah. So factor out 20x squared, which leaves me 4x minus 3. Did I do that right? 80x cubed, 60x squared. Set that equal to 0. And there are 2 inflection points. At x could be 0, or x could be 3/4. So the y-coordinate where x is 0, go back to the original, just 1. And now at 3/4, f of 3/4. Oh, I don't know. 4 times 3/4 to the 5th minus 5 times 3/4 to the 4th plus 1. Actually, I think that does work out. That's about 1/2. So in purple, when x is 3/4, y is about 1/2. That's 1 inflection point. Notice the x equals 0, it's critical and it's inflection. So 0, 1 is both critical and inflection. Sure. And so let's do our intervals. With 2 inflection points, you got 3 intervals. Over which we're going to test the second derivative to conclude something about concavity. So we have left of 0 between 0 and 3/4, and then to the right of 3/4. So take f double prime of -1, and it's positive times negative is negative, concave down. And in here, f double prime of, say, 1/2 is still negative, positive, negative. Yes. It's concave down on both sides. And here, f double prime of 1 is positive times positive. It's positive, concave up. So if we put all this together, yep. Increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. And so that was a good problem because it showed you could have a critical point which is also an inflection point. Good problem. Sorry for the messy arithmetic. So pick up with 31, and I will see you Friday.